Hello there and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us far beyond city lights and rustling curtains, past the buzz of phones and the clink of evening dishes, past even the moon's calm glow. We're drifting into something far older, far grander. Tonight we'll be floating through the cosmos, following the long, slow birth of galaxies, the swirling islands of stars that hang in the dark like jeweled lanterns in a velvet sea. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for that gentle, comforting hum in the background. Perhaps your cat is already curled up beside you, or you've got a warm cup of tea within reach. Wherever you are, let your shoulders drop just a little more. Let your thoughts slow like leaves floating on a still lake. Take a deep breath in and out. Competitiveness, you see, didn't always look the way it does now. The elegant spirals, the golden arms, the soft glowing cores of galaxies, they weren't always there. Long ago there were no stars, no clusters, no great gatherings of galaxies sprawling across the night. There was only a silent sea of particles humming gently, waiting for time to stretch it open. Galaxies are the grand storytellers of the universe. Each one holds the memory of countless generations of stars, born, burned, and gone. Some are young and bright, bursting with newborn suns. Others are ancient and quiet, wrapped in old starlight like a grandmother's shawl. And all of them, every shining spiral and lumpy blob, began as something much smaller, much simpler. A little pocket of possibility. So tonight, we'll follow those stories from their very beginning. From the quiet after the Big Bang, through the long cosmic dark, and into the first moments of light. We'll float beside clouds of gas as they collapse into stars. We'll watch galaxies spin themselves into shapes, some neat and elegant, others wild and chaotic. And we'll peer into the future too, to see where this great cosmic dance might be going. Proportional, but we'll do all of it slowly, gently. There's no need to rush. Exactly where you need to be, breathing, listening, floating with me just beyond the edge of thought. Slaughtered, let's begin this quiet journey together. Imagine for a moment that you're looking up at the night sky. Not through a telescope, not even with science in mind, just looking. Maybe you're lying on a blanket in the grass, or peeking out your window at midnight. The stars seem still, peaceful, but beyond that stillness is movement, slow, immense, and older than time as we know it. The light that touches your eyes tonight might have travelled for millions, even billions of years to get here. Some of it left when dinosaurs still roamed the earth, some when Earth itself was young and quiet, and some, even older still, comes from galaxies whose light began its journey when there were no galaxies yet in our corner of space. And beautiful thing about looking up at the stars, you're not just seeing distance, you're seeing memory, a record of how things were, not how they are. Each point of light is a message in a bottle, drifting across the cosmic ocean. And galaxies, those vast cities of stars, are the authors of many of those messages. They don't just shine, they evolve, they collide, they grow, and sometimes they even fade. Some are so large they could swallow 100,000 Earths across in a single spiral arm. Others are small and scrappy, held together by threads of gravity and luck. And they come in so many forms: elegant spirals, featureless ellipses, lopsided irregulars like smeared fingerprints across space. But they all began the same way, in darkness, in silence, in the thin strands of gas and invisible matter that wove the early universe like a cosmic loom. Tonight, as we follow their story, we'll pause often, not just to learn, but to feel. To drift gently between thoughts, to let your imagination settle into the vastness. You don't need to remember every fact or name. Let the ideas wash over you, like waves at night, soft and steady. And if you happen to fall asleep partway through, that's perfectly okay. The universe will keep unfolding without you. That's the gift of galaxies. They don't mind if you rest. They've been around for billions of years. They can wait a little longer. So here we are, at the threshold. The stars are waiting. The dark is deep but gentle, and just beyond it, the first galaxies are stirring, quietly into the cosmic story of how they came to be. Let's begin with nothing. Not the quiet nothing of a dark room, or the nothing of an empty field at night, but a true nothing. No stars, no galaxies, not even atoms. Just a hot, dense, endlessly compact sea of potential straining at the seams. And then, everything. In the first few moments after the Big Bang, the universe was a soup. Not of noodles or broth, but of energy. Blazing, formless, raw energy. Temperatures were unimaginably high, trillions of degrees. So hot that even the particles that make up protons and neutrons couldn't hold together yet. Quarks and gluons, like dancers waiting for the music to slow, swirled freely through space. But the universe wasn't still. It was expanding, rapidly. Faster than you can picture. Imagine the entire observable universe growing from smaller than a speck of dust to the size of a grapefruit in less than a blink. This phase, called cosmic inflation, stretched space so quickly that tiny fluctuations, ripples in the density of energy, were frozen in place like wrinkles in fabric. These little ripples were important. They were quiet, uneven, and at the time almost meaningless, but they would become the seeds of everything. As the universe expanded, it cooled, and in that cooling, things began to settle. Quarks paired up into protons and neutrons. Light tried to move, but was scattered endlessly by a fog of particles. The cosmos was still bright, in theory, but in practice, light couldn't get far. The universe was glowing, but blind. Then came nucleosynthesis, a lovely word for a very brief moment. Within the first few minutes, simple atomic nuclei formed: hydrogen, helium, a dash of lithium. The lightest elements were forged in the heat, setting the chemical stage for everything that would come later. But atoms were still incomplete. Electrons, which normally circle around nuclei like tiny moons, couldn't settle down just yet. The universe was too hot. So, for nearly 400,000 years, everything stayed as a hot plasma, ions and electrons in a constant frenetic dance, crippling no stars, no planets, no galaxies, just expansion, just soft, seething energy and slowly declining heat. It sounds empty, but it wasn't. It was full of potential. In those early ripples, the slightly denser patches of plasma, gravity began to do what gravity does best. It pulled, not quickly, not loudly, just gently enough to draw matter together. Slowly, those regions would grow. They would pull in more gas. They would become halos of invisible dark matter, quietly preparing for what came next. And then at last, the fog lifting. Now that was a moment worth pausing for. Roughly 380,000 years after the Big Bang, the universe cooled just enough for something marvellous to happen. Electrons and protons could finally settle down and combine into complete atoms. Simple hydrogen, gentle helium. The dance floor of the early universe finally had room to breathe. This event is called recombination, though technically it was the first time these atoms had ever formed, so there was nothing to recombine. But the name stuck like a well-worn sweater that's slightly misleading but still comfortable. Marvellous came clarity. Light had been trying to move freely through the universe all along, But in that thick plasma, it was constantly bumping into particles, ricocheting in every direction. Once the atoms formed, that scattering stopped. Suddenly, light could travel freely. It stretched out, filling the universe with a glow that we still see today, the cosmic microwave background, or CMB. This isn't just leftover light, it's a baby picture of the universe itself, a frozen snapshot of what the cosmos looked like when it first became transparent. Gentle swirls, tiny temperature variations, the same little ripples seeded by inflation now visible as faint, warm and cool spots across the sky. Exquisite detail with satellites like COBE, WMAP and Planck. We've painted portraits of the early cosmos, not with brushes and pigments, but with microwaves and mathematics. And every pixel in that portrait tells a story of density, of gravity, of time just beginning to stretch its legs. But despite all this change, the universe was still mostly empty. No stars, no galaxies, just a gentle bath of hydrogen and helium, quietly cooling. Gravity, however, was patient. In the denser regions, those tiny overdensities spotted in the CMB, matter began to gather. Dark matter formed invisible halos, and gas followed. Slowly, very slowly, the great cosmic structures began to form. These weren't galaxies yet. They were more like whispers of what was to come. Small clumps, little clouds, the seeds of future stars. And so the universe entered what scientists call the cosmic dark ages, a time after the glow of the CMB, but before the first stars flickered into being. Space was quiet again, transparent now, yes, but dark. A silent theatre, waiting for its first act. Fiberglass, no starlight, no planets, just the soft hush of gas and dark matter, slowly assembling, biding their time. To think of darkness as a beginning, but here, in the calm after recombination, it was. The first true structures of the cosmos were gathering their breath. Confiscated, the lights would come on. Now, the curtain has lifted. The glow of the cosmic microwave background has faded into a gentle afterthought, and the universe, now transparent, finds itself bathed not in light, but in darkness. This was not a darkness of absence, but of anticipation. A velvet hush stretched across billions of light years. The cosmic dark ages had begun. At first glance, this seems like a pause, a quiet intermission between the brilliance of the Big Bang and the first sparkle of stars. But within that silence, slow and steady things were stirring. The universe, now about 400,000 years old, had cooled significantly. Temperature dropped to a point where atoms, mostly hydrogen and helium, moved gently through space, unburdened by the constant collisions of earlier eras. These atoms drifted, collecting in slightly denser areas shaped by gravity. And gravity, ever the patient sculptor, was busy. In those slightly denser pockets, seeded by inflation and traced in the cosmic microwave background, matter began to fall inward. It didn't happen quickly. These were no sudden collapses or dramatic explosions, just a soft settling, like dust gathering in the corner of a quiet room. Dark matter led the way. Though we cannot see it, dark matter outweighs ordinary matter by roughly 5 to 1, and it doesn't interact with light. Instead, it forms invisible halos, massive structures that pull in gas and guide the shaping of space itself. These halos are like scaffolding, reaching through the vastness like an unseen lattice. And into them, the ordinary matter, the hydrogen, the helium, began to flow. The cosmic web was slowly taking form. Forbidden, no light. There were no stars to shine, no galaxies to glitter, just clouds of gas, slowly growing denser within these hidden cradles. If you could somehow stand in the middle of the universe during this era, though of course there was no middle to stand in, you'd see nothing. No sparkle, no suns, just the gentle breeze of particles, the dark embrace of expanding space, and the soft hum of gravity drawing threads together. Dark, it wasn't still. Inside those deepening wells of gravity, gas was cooling, compressing, gently folding in on itself. And as it compressed, it heated. Like hands rubbing together on a cold night, the atoms began to warm from the pressure of their gathering mass. Soon, though soon here means hundreds of millions of years, some of these clouds would reach a critical point. Their centers would become hot and dense enough for something miraculous to happen. Position fusion, stiffness, and when that spark finally lit, the darkness would end. Somewhere in that vast and silent dark, the first sparks were beginning to form. The clouds of hydrogen gas, slowly sinking deeper into the wells carved by dark matter, grew denser, tighter, hotter. And eventually, in one quiet corner of the early universe, a miracle happened. Plage. The atoms at the centre of one of these clouds became so compressed, so warm from their fall into gravity's arms, that they fused. Hydrogen nuclei combined into helium, and in that fusion, energy was released. Propane, at last, light. These weren't gentle stars like our Sun. The first stars, called Population 3 stars, were monsters, massive, wild, and short-lived. Born in an environment untouched by heavier elements, they grew quickly and burned fiercely, some hundreds of times more massive than the Sun. They radiated searing ultraviolet light, casting the first shadows across space. TARS didn't live long, just a few million years, a blink in cosmic time. But what they lacked in longevity, they made up for in consequence. Their brilliant radiation began to change the universe around them, tearing apart surrounding hydrogen atoms and reionizing the intergalactic medium. This marked the beginning of the epoch of reionization, when the fog of neutral hydrogen was cleared once again, but this time by the fierce light of stars. And when these stars died, oh, what a death! Many exploded as supernovae, scattering their ashes across space. Some collapsed directly into black holes, forming the seeds of the giants we see today at galactic centers. Before, perhaps most importantly, these stars created something entirely new: heavier elements. In their fiery cores, hydrogen was fused into helium, and then into carbon, nitrogen, oxygen, and beyond. Before them, the universe had only been light and hydrogen. After them, it had the ingredients for planets, for water, for life. These explosions seeded their surroundings with the materials that would eventually form second-generation stars, ones with a touch more complexity, stars like our Sun. Monitored from these ancient beacons still echoes faintly in the cosmos. We've never seen one directly, they lived and died long ago, but their fingerprints linger. In distant galaxies, in ancient starlight, in the chemistry of our own solar system. Northeastern Mick Dark Ages ended not with a bang, but with a blaze. The quiet became illuminated, not all at once, but in waves, first here, then there, like embers catching in a field of tall grass. And the universe was never dark again.
So now the lights have come on, but not like the gentle flicker of a candle or the slow rise of the morning sun. The first stars were more like bonfires in the dark, fierce, bright, and short-lived. They were born into a universe that had never seen light before, never felt heat, never known complexity, and they arrived with a kind of beautiful violence. These were the Population 3 stars, the very first stars to form in the cosmos, and they were unlike anything we see today. Were enormous. Many of them hundreds of times the mass of our Sun. Without heavier elements, what astronomers call metals, even if they're things like carbon and oxygen, there was nothing in these early gas clouds to cool them down effectively. So instead of breaking into smaller pieces, the clouds collapsed into fewer, bigger stars. Imagine a cloud of gas the size of a small galaxy, folding in on itself, not into thousands of stars, but just a handful, each one a titan. Each one burning hot and blue-white, pouring out ultraviolet radiation into the darkness. These were the first street lamps of the universe, harsh, unfiltered, and unstoppable. They lived fast. Plumbing of their mass, they raced through their nuclear fuel. A star like our Sun will live for 10 billion years, but a Population 3 star, maybe just a few million. A cosmic flashbulb. Brief but transformative. And when they died, they did so with grandeur. Some collapsed directly into black holes, silent and invisible. Others exploded as pair instability supernovae, a rare and particularly energetic kind of stellar death. These explosions didn't just scatter elements, they completely unmade the star, leaving nothing behind, no remnant, just a shockwave, and a spray of newly forged atoms hurled across the universe.
Those atoms, carbon, nitrogen, oxygen, iron, were the first of their kind. Before these stars, the universe was made almost entirely of hydrogen and helium, but in their lives and their deaths, these early suns created the ingredients that future generations of stars, planets, and life would be built from. Directly seen a population 3 star, their fingerprints are everywhere, in the faint chemical traces of the oldest known stars, in the background glow of ancient galaxies, in the theoretical models we've built to trace their brief but brilliant existence. Businessman's first act of creation, and like many first attempts, they were raw, bold, and completely unforgettable. If you could drift close enough to one of these first stars, though no spacecraft ever could, you'd be bathed in a radiation so intense it would feel like standing inside a furnace made of blue fire. They were not gentle suns like ours. These stars didn't twinkle, they roared. Blankets, their ultraviolet light cut through the surrounding hydrogen like wind through mist, breaking apart atoms and reshaping the invisible web of the early universe. They created ionized bubbles, regions where the hydrogen atoms were stripped of their electrons, leaving behind charged plasma that glowed faintly in ultraviolet. And as more stars formed, these bubbles grew and overlapped, slowly clearing the once neutral cosmos into a lacy structure of glowing gas and still dark voids. This wasn't just a light show, it was the first remodeling of the universe's structure, a cosmic awakening. Galaxies had not yet formed in any recognizable way, but these stars were already shaping the environment that would cradle them. And while each population 3 star lived alone, their legacy would ripple outward. They set the stage for the second generation of stars, population 2, made from gas that had been touched by heavier elements. These stars were a little smaller, a little longer lived, and a little closer to the kinds of stars we see today. Some of those second generation stars are still with us, quietly glowing in the outer reaches of our galaxy's halo. They're like elderly storytellers, holding the chemical memories of a time before galaxies had names. Bilingual talk then, there were no names, no maps, just the raw unfolding of the cosmos. The deaths of population 3 stars also planted the seeds of something else, something massive and utterly invisible. Some of these stars collapsed not into fiery explosions, but directly into black holes. These might have been the first supermassive black hole seeds, the quiet beginnings of the enormous gravitational monsters that now sit at the centres of galaxies, including our own. Imagine that. A brilliant, short-lived star collapses into darkness, and over billions of years it feeds and grows, eventually anchoring an entire galaxy, from light to shadow, and from shadow to structure. So much of what we know of what we are comes from these first stellar experiments. The calcium in your bones, the iron in your blood, the oxygen in every breath, all of it forged in furnaces you've never seen, in stars that died before our galaxy was even born. The first stars were not just the universe's first light, they were its first artists. They sculpted matter, they painted with elements, they wrote the opening lines of every cosmic story to come. And though their time was brief, their echoes still travel through space, in starlight, in the atoms around you, and perhaps in the quiet awe you feel when you look up at the stars and realize just how far that light has come. Now that the stars had awakened, the universe began to change, not just in brightness but in structure. The light was not alone, it came bundled with gravity, heat, and motion. Slowly, like snowflakes drawn toward a slope, the pieces began to gather. And what they were building, quietly, invisibly, were the first galaxies. But to understand how galaxies came to be, we need to look beneath the stars, beneath the clouds, beneath even the atoms. What we find there is dark matter, the invisible scaffolding of the universe. Dark matter doesn't shine. It doesn't reflect, absorb, or scatter light, but it has gravity. And in the early universe, gravity was everything. Those faint ripples we spoke of earlier, tiny fluctuations in density frozen into space by cosmic inflation, those became wells. And dark matter flowed into them. The result? Enormous dark matter halos, invisible yet massive, pulling in the ordinary matter like dust into a basin. Imagine a spiderweb strung across the sky, made of silk so fine you can't see it. Only the dew clinging to the strands. The dew is baryonic matter, hydrogen and helium gas. The web itself is dark matter, quietly shaping the structure of the cosmos. Within these halos, gas began to gather. It cooled, it collapsed, And at the dense centers of these invisible spheres, stars formed. Not just lone stars now, but groupings, clusters, swarms of light gathering around gravitational hubs. These were the proto-galaxies, the ancestors of the spirals, ellipticals, and irregulars we see today. They were messy, clumpy, far from the grand elegance we might imagine, but they were real. Small galaxies, mere fractions the size of the Milky Way, formed and began to merge. Some smashed together in violent collisions, others danced in spirals, orbiting and feeding off one another. Was the beginning of hierarchical structure formation, a slow assembly line of galaxies, merging and growing through cosmic time. Small systems collapsed first, then combined into larger ones. Like nesting dolls in motion, the universe built its cities of stars one layer at a time. Matter continued to play its invisible role, guiding motion, shaping galaxies, and helping them survive the chaos of early collisions. Without it, galaxies might never have formed. Stars might have scattered into lonely paths. Planets and life might never have happened. And while we cannot see dark matter directly, we know it's there. We see its pull in how galaxies spin, in how light bends around clusters, in the quiet fingerprints it leaves on the cosmic microwave background. It's like the bass line in a piece of music. You might not hear it clearly, but without it, the melody would fall apart. So here, in the soft glow of second-generation stars, within swirling clouds drawn by unseen hands, the first galaxies were born. Spiral or elliptical, they didn't have names or shapes that made sense, but they were the raw material of everything. Come. The universe was waking up, and it was beginning to build. Now that the universe had begun to assemble its luminous islands, these early, messy proto-galaxies, the real work of galaxy building could begin. You might imagine galaxies growing like plants, slowly blooming outward from a central seed, but in truth their growth was fed by a kind of cosmic nourishment, a quiet, steady river of gas flowing through space, not a raging flood, but a persistent, invisible current. This process is known as cold accretion, and though it might sound technical, it's surprisingly poetic. You see, the galaxies didn't just sit passively, hoping for stray clouds to wander in. They were embedded in a vast, interconnected web of structure, an immense, three-dimensional lattice of dark matter and gas, called the cosmic web. Like veins branching through a body, these filaments stretched across the universe, channeling matter from the emptier regions into denser nodes. Along these filaments, streams of hydrogen gas flowed, thin, cool, steady. Cold in this case doesn't mean icy, it means not hot enough to resist collapse. If the gas had been too hot, heated to millions of degrees, it would have floated, expanded and resisted gravity. But cold gas, just a few thousand degrees, is cooperative, it falls inward, it feeds. As the gas reached the centers of dark matter halos, it didn't crash in violently, it slipped in like mist down a mountainside, spiraling into the growing galaxy. There, it collected in reservoirs, some staying suspended in large halos, some cooling further and raining down into disks where new stars would soon be born. This cold mode accretion was the dominant way galaxies grew in the early universe, especially smaller ones. Larger halos with deeper gravity wells would sometimes shock heat incoming gas, creating hot accretion, which is more chaotic and less efficient. But cold accretion, that was nature's quiet, graceful delivery system. It's a bit like rainwater flowing through the roots of a forest. The galaxy is the tree, the gas is the rain, and the cosmic web is the soil and aquifers beneath it all, channeling every drop with ancient patience. And this wasn't a one-time event. These streams flowed for billions of years, feeding galaxies, fueling star formation, shaping disks, creating arms and bulges and halos. Unresolved today in the modern universe, traces of this process continue. Though harder to detect, astronomers have found long, cold filaments of gas stretching toward galaxies, like cosmic umbilical cords that never quite got cut. Flushing. So if you ever look at a photo of a spiral galaxy, graceful, swirling, luminous, you're not just seeing stars, you're seeing the quiet end of an ancient river, a galaxy that was fed by threads of the universe itself. Let's stay for a moment inside that quiet stream, those delicate rivers of hydrogen flowing across space. Though we often imagine space as empty, These filaments of cold gas were rich with potential. Each atom, drifting inward, carried with it the future sparkle of a star, each molecule a whisper of future worlds. As the gas funneled into the growing centres of proto-galaxies, it began to spiral, flattening out like a dancer pulling in their arms to spin faster. This conservation of angular momentum is what eventually gave galaxies their graceful, swirling shapes. But at this stage, the motion was subtle, more a stirring than a spin. The gas wasn't all smooth. It clumped, it buckled, it was stirred by gravity and jostled by supernovae from the first waves of stars. These interactions created areas of high density, places where the gas cooled even further and began collapsing into new stars. And with each new star came light. Some stars stinned to burn for billions of years, others were larger, brighter, and destined for fiery ends. But all of them helped shape the growing identity of their host galaxy, heating the surrounding gas, blowing bubbles in the interstellar medium, and regulating how much material could keep falling inward. Blackmail, this constant balance between gas inflow and stellar feedback, is what made early galaxies so dynamic. They weren't quiet collections of stars, they were ecosystems, pulsing with energy, giving and taking, building and breaking. At the centre, cold accretion continued from the outskirts. Picture a fountain in slow motion, water drawn upward, then falling inward along elegant arcs. Now flip that image. Gas flowing from cosmic filaments into galactic cores, like invisible hands feeding a fire from beneath. Eventually, some of this gas settled into a rotating disk, a broad, flat plane of stars, gas, and dust. In some cases, the beginnings of spiral structure began to emerge. In others, things remained more chaotic. Not all galaxies would grow the same way, but all of them, every single one, was fed by this same process, the quiet, patient delivery of gas through the veins of the cosmos. There will with spring and op, ingested is sponsbon, and spoground to design to reach the galaxy. Time, the Mitarelli time here, the whirlwood would new block, picker out it onto two Likika publishiv ses. The spiral's filaments would be supt of a brain, with the new boarding through the Chi design result. Time, with uniting star scrout, and ungested design, to me with Clogord wales to the rise and said. Now time, though story area, the person Holy's tone, but he will with the included for that time. The stars would still debil a block, and so rolled falling in dendies well, included here distending and bad, the filaments of jobstat of manages, in seeing places house about 2 years large, from the darky appainingly. Then, being siling out in some easily fetzes, and like on 9 jobs and times and their year, the folks by not in dire as they do that, what is into a life flooring tops that bald, the least floor lemerns close the blong, and colligated by historians from the stars. The moment structures, the life parencies forthing from cistern, the collings of hair that lightive his motions to link the auditors. The include stirs on their future desteries to learning beans, and knots combaxies. This turn would turn to devise to see their destrex, you conceive the new mediums of the motions to plose. Things clean into the change of the disc writing and marga. In sinding, the first word so brave to long name test. Let's drift now into one of those quiet discs of gas, those newborn galaxies just beginning to catch their breath. From a distance, they look soft, cloudy, like gentle swirls of smoke against a dark backdrop, but inside, they're bustling with activity. For nestled within these clouds are the places where stars are born. These are the stellar nurseries, dense, cold regions of gas and dust where gravity takes hold and something luminous begins to grow. They often start with nothing more than a ripple, a small disturbance in a gas cloud, caused by turbulence, a passing shock wave from a nearby supernova, or even the spiral motion of the galaxy itself, can compress part of the cloud just enough for gravity to gain the upper hand. Once that happens, a quiet race begins. Gravity pulls the material inward, the gas resists, tries to push back with pressure, but if it cools quickly enough, it loses the fight, the cloud collapses, the centre grows denser. And at some point, when the pressure and temperature rise high enough, hydrogen atoms begin to fuse into helium. A star is born. But not just one. These clouds often fragment, giving birth to dozens or hundreds of stars at once. Some will be tiny red dwarfs destined to glow for trillions of years. Others will be massive blue giants burning out in a few million. Each is born from the same cloud, like siblings in a vast cosmic family, but they live vastly different lives. And while they grow, the nursery glows. Dust in the surrounding gas absorbs the intense radiation from newborn stars and re-emits it in infrared light, making these regions shine with a warm, hazy glow. From afar, they look like lanterns hung in the arms of galaxies, soft, glowing knots of stardust. Here on Earth, we can see these nurseries too. Places like the Orion Nebula, only about 1,300 light-years away, offer a peek into the process still unfolding today. There, gas curls like smoke. Young stars sparkle behind curtains of dust. It's a miniature version of what those early galaxies were doing on much grander scales. Star formation isn't fast. It takes millions of years for clouds to collapse, stars to ignite, and feedback to shape the region around them. But it's relentless. One cloud leads to another. One generation of stars triggers the next. And while it may seem peaceful from a distance, up close, these nurseries are anything but calm. Shock waves, stellar winds, radiation pushing on dust like sunlight on a sail, newborn stars reshaping their cradle even as they rise. It's a dance, one of gravity and pressure, light and shadow, and it plays out billions of times across the sky. As stars take shape inside these glowing clouds, they begin to reshape the very space they were born into. The newborn giants, those hot blue stars with masses dozens of times greater than the Sun, don't stay quiet for long. Their radiation is intense, their winds, streams of charged particles streaming outward, begin to push back the surrounding gas, carving out bubbles and corridors in the cloud. It's like a candle flame melting a hole through fog. Freezes is more than just beautiful, it's essential. The very act of forming stars helps limit how many more stars can form nearby. If a region becomes too dense, it collapses, but if the newborn stars burn too hot, they blow the cradle apart. It's a balancing act, creation and disruption, side by side. Some of these massive stars will end their lives in violent supernovae. When they do, they blast out shockwaves that ripple through the cloud, compressing it in some places, scattering it in others. Sometimes these shockwaves act as a midwife, triggering the next generation of stars to form. Other times, they act like a broom, sweeping the region clean and ending the cycle for now. These processes, collapse, feedback, disruption, don't happen in isolation. Across a galaxy, thousands of star-forming regions might be active at once, some clustered in arms, others tucked in the outer reaches. Each one is its own tiny storm of creation. The result is a galaxy that breathes. Gas flows in from the cosmic web. It collects, it cools, it forms stars. Those stars in turn heat the gas, stir the medium, and limit further formation. Over time, the galaxy's ability to make stars rises and falls like a slow heartbeat. It's not a machine, it's an organism. And like all living systems, it has rhythms. Some galaxies are fast breathers, bursting with star formation for a few billion years before running out of fuel. Others take their time, stretching their gas supply across billions of gentle, glowing centuries. Frosting, and in these nurseries, across all this motion and feedback, patterns begin to emerge. Spiral arms sweep stars into elegant lanes, bars stretch across galactic centers, disks thicken, halos expand. It is structure from chaos, guided by gravity and time. You might think of a galaxy as a finished object, something static, captured in a telescope photo, but in truth, it is always in motion, always growing, changing, stirring. A galaxy is less a thing and more a story, told in dust, gas and starlight, flaming, and this chapter, the era of stellar birth, was just beginning to unfold. As galaxies continued to grow, something elegant began to take shape. From the swirling chaos of gas and star-forming clouds, a pattern began to emerge. Not rigid, not permanent, but beautiful nonetheless. The beginnings of a spiral. Peeping all at once, these early galaxies were still irregular, clumpy, asymmetrical, but under the quiet influence of physics, particularly angular momentum, they began to flatten, to spin, to form disks. When gas falls into a galaxy from the cosmic web, it doesn't simply drop straight in. It twists, it turns, it arrives with a slight rotation, a direction, and just like a spinning skater who pulls in their arms to spin faster, the gas begins to conserve and concentrate that rotation. Phased over millions of years, this slow turning stretches the galaxy into a thin, rotating disk. New stars continue to form. The spiral arms that begin to appear aren't rigid structures, they're more like traffic jams in a circular highway. Areas where stars and gas briefly slow down, bunch together, and create density waves. As material moves through these arms, it compresses. Gas clouds squeeze together, new stars ignite. And so the arms shine more brightly, not because they're made of different stuff, but because they're lit by the glow of fresh starlight. It's a bit like a ripple in a pond. The water isn't moving outward in a ring. It's the wave that travels, not the water itself. In the same way, spiral arms are waves of density, not fixed lanes of stars. These patterns can be breathtaking. From the outside, a spiral galaxy looks serene, balanced, almost painterly. But from within, it's bustling. Gas flowing inward, stars rotating at different speeds, arms sweeping around like galactic clock hands that never quite line up. The Milky Way, our own galaxy, is one such spiral. We can't see it from above, we live inside one of its arms. But by studying other galaxies and mapping our stars with great precision, we've pieced together its elegant structure. A central bulge, long, graceful arms, a halo of stars and dark matter beyond. Flooding, and it all begins with rotation, with gentle motion, with the quiet insistence of physics shaping clouds into spirals, arms, and glowing lanes of life. So when you look at a photo of a spiral galaxy, when you see those soft swirls curving out from a bright center, you're seeing a moment in time, a freeze frame of motion, a still shot of something that's spinning, drifting, evolving. It is shape born from motion, pattern born from flow. And in the heart of that pattern, stars, gas, dust, and the possibility of life. If you were to float inside a spiral galaxy, not just outside it looking in, but gently adrift among its stars, you might not even notice the pattern at first. It would feel like a scattering of light, stars around you in every direction, some near, some impossibly far, a gentle gradient from brighter to dimmer, warmer to cooler. The arms, from the inside, are not sharp boundaries. They're gentle currents, slow shifts in density that guide the stars and clouds like eddies in a wide river. But over time, if you could trace the paths of those stars, if you could follow their journeys like ribbons in wind, you would see the spiral unfold, not because the stars are arranged like painted stripes, but because the whole disk moves with a kind of collective memory, the heart of spiral structure, motion woven into shape. The spiral arms don't stay fixed, they wind and unwind, they drift and evolve. Over millions of years their pattern can shift. Galaxies don't sit still. They're dynamic and alive in a quiet way. And yet, despite that motion, some spirals persist, particularly those with bars, elongated structures stretching across their centers. These barred spirals, like our Milky Way, have a central structure that helps funnel gas inward, fueling both star formation and the quiet growth of the central bulge. Before bars aren't permanent either. They rise, evolve, and sometimes dissolve. But while they last, they help regulate a galaxy's rhythm, like a conductor keeping time while the stars play their parts. Confined the disk itself, the flat plane where most stars reside, isn't perfectly smooth. It ripples, it thickens, it can warp. Tidal interactions with nearby galaxies, or waves from old collisions leave their marks. Even in the calmest galaxy, you'll find history etched in the starlight. Forged of the disk can vary too. Younger stars tend to live in the thinner regions, closer to the galactic plane, while older stars drift into thicker, more diffuse layers. The result is a stellar population gradient, a soft transition from bright, youthful arms to the quieter outer reaches. And beyond the disk, a halo of old stars and even older dark matter. The galaxy, like an island, is surrounded by a sea of invisible influence. This whole structure, disk, bulge, bar, halo, is not inevitable. Not all galaxies become spirals. But when they do, it's a sign that order has emerged from motion, that the chaos of early formation has begun to settle into rhythm. Those arms curving outward know this. They are not fixed roads but flowing streams, not frozen structures but slow dances of stars and gas.
Not all galaxies are graceful spirals. Some are older, rounder, quieter. These are the elliptical galaxies, massive glowing orbs of stars that have long since stopped making new ones. They don't spin like disks, they don't have spiral arms or dramatic dust lanes. They simply are, still, luminous, and full of memory. To understand how a galaxy becomes elliptical, you have to imagine a kind of cosmic collision. Two spiral galaxies, beautiful, rotating, full of gas and new stars, drawn together by gravity. Over millions of years they approach, tugging at each other, stretching and warping like dancers reaching for an embrace. Then, finally, they meet, eatly. Not gently, not nihilent force of titanic clouds colliding in slow motion. Strengthening being tiny compared to the space between them, rarely collide, but their orbits are disrupted. Gas clouds smash into one another, the disks collapse. The neat structure of the spirals dissolves. What remains is a puffed-out, three-dimensional cloud of stars. A new structure, one without a clear plane or pattern. The Zishan. This is how many elliptical galaxies are formed, through mergers. And when that merger is especially violent, it triggers something called a starburst, an intense period of star formation fueled by the collision of gas clouds. It's a final blaze of brilliance before the gas is used up or blown away. After that, with little fuel left, the galaxy quiets down. The stars grow older, the light reddens, the structure settles into something round, diffuse and gently glowing. End to host some of the most massive black holes at their centres, perhaps because of their violent pasts, perhaps because their central bulges grew rapidly during mergers. Either way, they carry a kind of quiet weight, the cosmic equivalent of an old city, full of grand buildings and deep history, but fewer people walking the streets. They range in size from giant ellipticals, containing trillions of stars, to dwarf ellipticals, which are small, dim, and difficult to detect. But regardless of size, they share a shape. No spiral arms, no disks, just ellipses, blurred spheres of stars with little gas or dust to speak of. And while spirals twinkle with the blue light of new stars, ellipticals glow with the red and gold of ancient ones. They are galaxies that have already written most of their story. But not all galaxies take this path. Blinked, some never quite settle into a clear shape at all. And that's where we'll go next. Not every galaxy settles into a tidy spiral or mellows into a smooth elliptical. Some resist symmetry altogether. They twist, they tangle, they bloom in odd, asymmetrical shapes. These are the irregular galaxies, the cosmic rebels, the strange ones, the places where structure is still a work in progress. Irregular galaxies often arise from disruption. Maybe they were small to begin with, born on the outskirts of cosmic filaments where matter is scarce and gas flows uneven. Or maybe they were once spirals or disks, but were nudged too hard by a passing neighbour, pulled, twisted, stirred by gravity into something lopsided. Unlike spirals, they have no well-defined arms. Unlike ellipticals, they have no clean, rounded shape. They are clouds of stars and gas, caught in a moment between formation and transformation. Some shine with the bright blues of newborn stars, others flicker with age. Contentious, they may be small, but they are not simple. Some of the most active regions of star formation occur in irregular galaxies. Why? Because their gas hasn't yet settled into stability. It flows, collides and compresses more freely,
unhindered by neat structure, as the cosmic wildlands, regions where stars still burst into being unpredictably, and where gravity is still negotiating the terms of order. Flirting. Irregular galaxies are survivors. When a larger galaxy pulls in a smaller one, like the Milky Way, drawing on the Magellanic Clouds, the tidal forces stretch and distort the smaller object. The result is often irregular. Tails of stars pulled away, plumes of gas trailing behind like smoke from a candle. These disrupted remnants can orbit their captors for billions of years, slowly unraveling, slowly merging. Our own galaxy has left its fingerprints on several irregulars, and someday it will absorb them entirely. But irregular doesn't mean unimportant. These galaxies play a vital role in the grand ballet of cosmic evolution. They are the fragments from which larger galaxies build, the companions that trigger bursts of new stars, the explorers of galactic possibility. Some irregulars may eventually settle into something more orderly, others may be consumed, and some will simply drift, changing little for billions of years, glowing quietly at the edges of galactic clusters. Flooring our beauty lies in their unpredictability, in their refusal to conform. In a universe often shaped by symmetry and repetition, irregular galaxies remind us that creation isn't always tidy, that growth sometimes looks like chaos, that wonder can arrive unshaped, unfinished and still unfolding. And in the end, whether spiral, elliptical or irregular, every galaxy is part of a greater pattern, woven from stardust and silence, motion and memory. Up until now, we've followed galaxies as solitary beings, each forming from clouds of gas, shaped by gravity, lit by stars. But galaxies are rarely alone. They live in communities, vast gatherings of hundreds or even thousands, bound together by gravity across unimaginable distances. These are the galaxy clusters. Catastrophic the night sky, not with just a few stars, but with galaxies instead. Each glowing swirl a city of stars, each drifting gently in relation to the others. A galaxy cluster is a metropolis of galaxies, and at the heart of this city, heat, motion, and mass beyond imagining. Clusters form where the cosmic web knots itself most tightly. As the universe evolved, dark matter filaments pulled galaxies along their threads, gathering them into dense nodes where multiple filaments intersect. These intersections became the gravitational wells where clusters began to take shape. The galaxies within them don't sit still. They orbit one another, they move through hot gas, they interact, collide, and sometimes merge. But they are not drifting in empty space. Between them lies a vast invisible ocean, the intracluster medium, a hot diffuse plasma that makes up most of the cluster's baryonic mass. This gas is heated to tens of millions of degrees, not by stars but by motion. Galaxies falling into the cluster move fast, sometimes thousands of kilometers per second. The energy from this motion stirs the gas, creating pressure and friction that heats it to X-ray emitting temperatures. It glows not in visible light, but in high-energy rays that only special telescopes can see. And within this hot sea, galaxies navigate. Some pass through quietly, others are stripped of their gas, a process known as ram pressure stripping, leaving behind trails of material and halting future star formation. These quenched galaxies grow dimmer over time, fading from bright blue to muted red. Larger galaxies, especially those at the centers of clusters, can become giant ellipticals, swallowing smaller galaxies and growing massive cores. Some of the largest known galaxies sit at these cluster centers, anchoring their surroundings like massive stones in a quiet pond. Footing itself, it continues to grow. Slowly, it pulls in more galaxies, more dark matter, more heat. Over billions of years, small groups merge into bigger ones. Clusters become superclusters, gravitationally connected regions stretching hundreds of millions of light years across. Turbulence ease superclusters aren't tightly bound like clusters. Instead, they form great tapestries of galaxies, gas, and dark matter. The one we live in is called the Laniakea supercluster, a name meaning immeasurable heaven. Within it lies the Virgo cluster, and tucked inside that, the local group. And there, on one spiral arm of a modest galaxy, is us. It's humbling, really. Galaxies are already vast. But to see them gathered in groups, flowing toward each other through dark matter currents, it makes you realize just how immense and interconnected our universe truly is. You could hover above a galaxy cluster, not from a single point, but from a timeless vantage, watching over billions of years.
you'd see a slow, breathtaking ballet. Galaxies, glowing and spinning, drifting inward like petals on a vast tide. Some approach each other, pass close, and continue on. Others tangle, merge, and become one. All the while, dark matter halos overlap and stretch, guiding these motions with silent precision. It's easy to imagine the space between galaxies as empty, as though these spiraling giants were drifting through a great nothing. But clusters are filled with presence, not absence. The intracluster medium, that sea of superheated plasma, presses against every galaxy like an invisible wind. Eliminated tap into the cluster's heart. Their own gas is stripped away. This is ram pressure stripping, and it's not unlike holding a loose scarf out the window of a moving car. The pressure of motion through the medium pulls at the galaxy's gas, unspooling it into long tails that trail behind like ghostly ribbons. Over time, these galaxies become quieter. With their gas gone, they can no longer form new stars. The blue sparkle of youth fades, replaced by a soft amber glow. Older stars, still burning but without the fire of new life. These galaxies become what astronomers call quiescent, not dead, but resting. Their stories pause even as the cluster's motion continues. At the very centre of many clusters lies a giant, an enormous elliptical galaxy, swollen from centuries of mergers. Sometimes called a CD galaxy, it sits like a monarch at the heart of a swirling court. These galaxies can span hundreds of thousands of light years and contain trillions of stars. Their mass, their influence, their sheer presence, none of it is subtle. This motion and heat and mass, clusters are not chaotic. They are structured, balanced, held together not by walls but by gravity, gentle and persistent, threading through dark matter halos like the frame of a grand cathedral. Even more incredible, these clusters are themselves drifting, moving within larger structures we call superclusters, not bound tightly, but gently drawn together across cosmic scales. Our own Laniakea supercluster, for example, contains over 100,000 galaxies, all part of an immense flowing structure that stretches across 500 million light-years. And within Laniakea, all of those galaxies, including ours, are gently streaming towards something, a region called the Great Attractor, a gravitational anomaly so massive that it bends the path of entire galaxy clusters toward it. What exactly it contains remains, even now, somewhat mysterious. But what we do know is this: galaxies are not scattered at random. They gather, they move, they respond to each other. The universe has shape, large-scale structure, a cosmic geography mapped not with mountains and rivers, but with clusters and filaments, voids and flows. Blinds to live inside one of these galaxies as we do is to float quietly in the company of giants. Amidst all the grandeur of galaxy clusters and superclusters, nestled gently into one quiet corner of the cosmic web, is a small gathering of neighbours. It's not a cluster, not a supercluster, just a cosy family of galaxies moving through space together, bound by gravity and time. This is the local group, our galactic home. At the centre of this group are two giants, the Milky Way and Andromeda, separated by about 2.5 million light-years and slowly drifting closer. Each one is a spiral galaxy, each with its own halo of stars, gas and dark matter. They are the twin hearts of this community. Orbiting around them are dozens of smaller galaxies, some neat and spheroidal, others ragged and irregular. The Magellanic Clouds, for example, are two irregular companions to the Milky Way, visible from the southern hemisphere as smudges of light in the night sky. They are galaxies in their own right, full of stars and gas and mystery, trailing behind them faint ribbons of material stretched by our galaxy's gravity. Andromeda too has companions, smaller galaxies that follow its motion like moons around a planet. The local group in total spans about 10 million light-years and contains over 50 galaxies. It's not tightly packed. The space between galaxies is still vast, quiet, dark, but compared to the emptiness beyond, it is a cluster of warmth, a shared history. Alien years from now, that history will become even more entwined. The Milky Way and Andromeda are on a collision course, moving toward each other at roughly 110 kilometers per second. They are destined to meet in about 4 billion years. When they do, it won't be an explosive crash. Galaxies are mostly empty space, after all. Stars will pass each other like dancers on a vast stage, rarely touching. But their orbits will be stirred. Their structures will stretch and warp. The beautiful spirals will dissolve into tidal streams and shells. Eventually, after a long and luminous dance, the two galaxies will merge into one, likely forming a giant elliptical galaxy,
bright and puffy, glowing with the light of trillions of stars. This future galaxy already has a name, Milkomeda, priesthood, and even as that merger unfolds, the smaller galaxies of the local group may be drawn in, one by one, adding their stars to the growing collective. The whole group will become quieter, redder, more ancient. And though we won't be there to see it, this gentle future speaks to the ongoing evolution of the cosmos. Galaxies don't remain what they are. They shift, they grow, they merge, they fade. In the meantime, our place in the local group remains serene. The night sky is still full of companions, though they appear as faint smudges or distant sparkles. Every one of them is a neighbour. Every one of them is moving with us through the dark. We are not alone in the void. We belong to a small, quiet family. A cluster of light drifting together through the cold, and in that gentle drifting, a story continues. Between the bright spinning galaxies, between the clusters, the superclusters, and the delicate filaments of the cosmic web, there are vast spaces. Not just empty, not just dark, but truly sparse. Regions so wide, so quiet, and so low in matter, they are known as voids. These are the lonely deserts of the universe. And yet, even here, something stirs. Before we reach those deepest stillnesses, let's pause in the spaces between galaxies. Not the voids, but the threads. This is the intergalactic medium, or IgM. Undermined is made mostly of hydrogen, traces left over from the Big Bang, thinly spread across cosmic distances. It's not dense enough to form stars. It doesn't glow in visible light, but it's there. And it plays a quiet, vital role in the life of galaxies. Think of it as the connective tissue of the cosmos. Galaxies don't just exist in isolation. They exchange with their surroundings. They pull in gas from the IgM, fuel for future stars. And they return material too, through galactic winds, supernova explosions, and the outflows driven by black holes. This cycle of inflow and outflow is part of what we call the cosmic baryon cycle, a beautiful name for a process that regulates how galaxies grow, age, and change. The IgM is not perfectly smooth, it is laced with structure, low-density filaments, tiny clumps, even proto-clouds that may one day feed galaxies. In places it's been heated by quasars or stripped by galactic winds. In others, it remains cool and undisturbed. But how do we know it's there? The IgM doesn't emit much light, but it can block it. When the light of distant quasars, those incredibly bright galactic cores, passes through the IgM, some wavelengths get absorbed, especially those from hydrogen. This absorption creates patterns called the Lyman alpha forest, dozens, sometimes hundreds of small absorption lines in a quasar's spectrum. Each line is a whisper from a different cloud at a different distance. Together they trace the subtle structure of the IgM across billions of years and light years. They're like trees glimpsed in the fog as you drive down a long road, dim outlines, but clues to the terrain. To think of such emptiness as meaningful, but the IgM holds most of the universe's ordinary matter. Not stars, not planets, not people, but the invisible scaffolding between them. It is the ocean in which galaxies are ships, the sky in which galaxies are birds. Blackmail, and when we step further still, beyond the filaments into the true voids, we will find a silence even deeper. Now we drift further out, beyond the filaments, the clusters, and even the faintest strands of gas. Out here we find the cosmic voids. These are not small gaps between galaxies. These are vast cavernous spaces, spanning tens to hundreds of millions of light years across. In them galaxies are few and far between. The matter that does exist is so thinly spread it's practically undetectable. A single cubic meter might contain fewer atoms than you could count on one hand. And yet, they are not completely empty. Even here, threads of hydrogen, whispers of dark matter, lone dwarf galaxies drifting like lanterns through mist. It's the quietest part of the universe's large-scale structure. If the cosmic web is a sponge, then the voids are its holes. Regions shaped by the outward flow of expansion, where gravity never quite managed to gather enough matter to make anything substantial. These voids give the universe its texture, its depth, its breadth. Perfectly round. Some are elongated, some contain nested subvoids like smaller bubbles trapped inside larger ones, and they're not static. Over billions of years, as matter collapses into filaments and clusters, the voids grow larger. They expand, not by pushing out but by being left behind. The denser regions attract more matter, while the emptier ones simply drift apart. Strangely enough, studying these places of nothing teaches us a great deal. By measuring the size, shape, and distribution of voids, scientists learn how the universe is expanded, how dark energy behaves, and how the invisible scaffolding of dark matter has evolved over time. Voids also offer a kind of cosmic laboratory. With so little matter, they provide a quiet environment to study gravitational effects, light travel, and even the subtleties of the cosmic microwave background as it passes through. And while they may seem cold and indifferent, there's something deeply poetic about them. They are not failures of creation. They are spaces between songs, rests between notes. They give the universe its rhythm. Foreground, the galaxies sing, the clusters roar, but the voids listen. When you gaze up at the night sky, it's easy to focus on the bright things, the stars, the planets, the glowing clouds. But remember, most of the universe is space, stillness, quiet. And that silence, too, is part of the story. The galaxies drift, the filaments stretch, the voids expand, and the universe continues its slow, beautiful unfolding. Though galaxies often appear isolated and serene in images, like lone whirlpools in space, they live social lives. They move through neighborhoods filled with unseen currents, and sometimes they collide. Not all collisions are violent in the way we imagine. Most are slow, graceful even. Two galaxies drifting together across millions of years, drawn by mutual gravity. But make no mistake, these encounters change everything. Disponibly, this is the world of tidal forces and galactic cannibalism. Skyrocket and Galaxy approaches another. The gravity of each begins to pull on the other's stars, gas, and dark matter. These pulls are uneven, stronger on the side closest, weaker on the far side. This difference is what we call a tidal force. It stretches galaxies, warps their shapes, sends great streams of stars, tidal tails, arcing out like glittering ribbons. Some of the most dramatic galaxy images ever captured, long spirals unraveling, bridges of stars stretching across the dark, are snapshots of this process in motion. In some cases, the galaxies spiral around each other for a while, caught in a long gravitational waltz. In others, a larger galaxy simply consumes a smaller one. This is galactic cannibalism, not with teeth, but with tides. Galaxies has done this many times. Even now it's absorbing smaller galaxies from the local group. The Sagittarius dwarf galaxy, for example, is being torn apart by our galaxy's gravity. Its stars are already smeared into long streams across our sky, ghost trails of a galaxy slowly being swallowed. These processes, expected, they're part of how galaxies grow, through mergers and accretion, not just peaceful gas inflow. A large galaxy is not just a collection of stars, it's a record of past meals, of swallowed neighbours, of gravitational conversations written in light. These mergers are major, two galaxies of similar size colliding and forming a new, often elliptical galaxy. Other times, they're minor, a giant pulling in a companion, adding to its halo or feeding its central black hole. Mergers stir up gas. They can ignite starbursts, brief, intense waves of star formation triggered by the sudden compression of gas. They can also feed the active galactic nuclei, the brilliant, energetic regions powered by supermassive black holes, suddenly flush with new material. Ultimately, the while recorded in his genius, take including Preece, are spailing cowards for alders only. Fleeing, it's a bit like bumping a calm pond and watching ripples rush outward, except these ripples are made of stars and dust, and they last for hundreds of millions of years. Blackmail, and yet, amidst all this disruption, galaxies endure, they settle, they smooth out, they shine on. From the lone parrot or mutist, when you look at the night sky, you're seeing the product of countless such encounters, quiet mergers, forgotten cannibalism, the elegant consequences of gravity playing out on grand scales. Galaxies do not stay untouched. They are shaped by their histories, their scars are beautiful. So far, we've spoken mostly of what can be seen, the stars, the gas, the glowing disks and spirals. But the visible parts of galaxies are only the tip of something much larger. Surrounding every galaxy, hugging it like a gentle cloak, shaping it like invisible hands, is something we cannot see at all. Dark matter is not made of atoms. It doesn't reflect light. It doesn't glow. It doesn't absorb or scatter photons in any way. In every image you've ever seen of a galaxy, no matter how detailed or breathtaking, the dark matter is entirely absent to your eyes. And yet, it's there, quiet, present, powerful. We know it's there because galaxies don't spin the way they should. If you only count the visible stars and gas, the outer regions of a galaxy should rotate more slowly than the inner ones, but they don't. Instead, the stars at the outskirts move just as fast, sometimes faster, than those near the center. This tells us that something extra is pulling on them, something invisible, something massive, something we call dark matter. Each galaxy is surrounded by a dark matter halo, a roughly spherical region of unseen mass that can extend far beyond the edges of the visible disk. In fact, most of a galaxy's mass is dark matter, not stars or gas. You might picture the luminous part of a galaxy, what we can actually see, as the glowing core of a much larger invisible dandelion puff. Defiants aren't uniform. They have structure. They ripple slightly. They grow. They merge. They pull in regular matter, shaping the formation of stars, galaxies, and clusters. Without dark matter, galaxies might never have formed at all. In the early universe, it was the dark matter halos that formed first, small ones, growing from the tiniest fluctuations in density. These halos acted as gravitational wells, drawing in gas, triggering collapse, and allowing stars to form. Over time, smaller halos merged into larger ones, forming the scaffolding for galaxies, groups, clusters, and superclusters. This is why we call dark matter the scaffolding of the cosmos, not just metaphorically, but structurally. It's the unseen framework on which the visible universe hangs. And while we still don't know what dark matter is made of, whether it's a new kind of particle, a class of objects, or something even stranger, it behaves in predictable ways. It exerts gravity. It doesn't clump like ordinary matter. It rarely, if ever, collides with itself. It simply flows, surrounds, and holds. Imagine walking through a vast, foggy cathedral at night. You can't see the walls, you can't see the beams or the columns, but the way your voice echoes, the way your steps carry, the way the air presses against you, it all tells you the structure is there, that you're not in empty space. That is how galaxies exist within dark matter halos. They shine in the center of something vaster, quieter, and profoundly invisible.
Now let's stay with that image a little longer. Of a galaxy, luminous and graceful, sitting like a firefly in the heart of an invisible sphere. The dark matter halo that surrounds it isn't just a passive shell. It shapes everything galaxies grow, how they move, how they interact, even how they merge. Halos are not hard boundaries, they are gradients, with density highest at the center and fading outward like the soft echo of a bell. And it is within these gradients that galaxies take root. Smaller halos form first, gathering mass slowly from the surrounding universe. They host dwarf galaxies, or sometimes only gas. Over time they collide with other halos, merging like droplets of oil, and form larger halos, which in turn gather more gas and form larger galaxies. It's a quiet hierarchy of structure, unfolding over billions of years. What's remarkable is how much of cosmic history is dictated by these invisible shapes. From the early clumping of matter to the grand architecture of superclusters, everything rides on the geometry of dark matter. Every filament, every knot, every arc of galaxies across the sky is traced by a corresponding shape in the dark matter map. Playoffs, we cannot see these maps with our eyes, but we can reconstruct them. Using the motions of galaxies, the bending of light from distant sources, a phenomenon called gravitational lensing, and the large-scale distribution of mass, astronomers have pieced together these ghostly webs. The result is a portrait of the universe as it really is, a glowing surface stretched across an unseen framework. And perhaps the most poetic part? Even though dark matter dominates the mass of galaxies, it remains untouched by light. It moves through itself, and through ordinary matter, without resistance. Galaxies can collide, but their halos pass through one another, as if made of shadow. One of the most telling demonstrations of this came from observing the Bullock cluster. Two colliding galaxy clusters. The hot gas between them slammed together and slowed down, lighting up in X-rays. But the dark matter passed straight through, like wind through silk. This separation of visible mass and gravitational mass was a clear signal that dark matter is real and different. And so, in a strange and beautiful way,
The shape of the visible universe is not built by what shines, but by what stays hidden. It's a quiet truth that behind every brilliant galaxy is something silent. Bathrooms, think dark. Wilmington, that holds without ever being seen. Now that we've followed the quiet pull of dark matter across the cosmos, let's shift inward, to the very heart of galaxies. Because deep at the centre of most, if not all, large galaxies, there lies something small, dense, and unimaginably powerful. A supermassive black hole. Black holes as exotic, mysterious objects, strange leftovers from dead stars, cloaked in shadow, hiding in corners of the cosmos. And while that's true for stellar mass black holes, the ones formed from collapsed stars, supermassive black holes are something else entirely. They don't weigh a few suns, they weigh millions or even billions of solar masses, and yet they are no larger than our solar system in size. 1 billion suns, folded into a space smaller than a planetary orbit, a gravity so intense that not even light can escape. And somehow, nearly every large galaxy seems to have one. At the centre of our Milky Way, there's a black hole called Sagittarius A star. It weighs about 4 million times the mass of the Sun. We've never seen it directly. Black holes, after all, don't emit light. But we've watched the stars that orbit it. Over years and decades, astronomers have traced their curved, swooping paths, like marbles circling a drain. And from their motion, we've calculated the hidden mass they orbit. Sagittarius A star is quiet now, dormant, but it wasn't always. There are times in a galaxy's life when its central black hole becomes active, when it feeds. As gas falls into the black hole, it doesn't drop straight in. It forms a swirling accretion disk, heating up from friction and pressure, glowing brilliantly. This is what we call an active galactic nucleus, or AGN. Some AGN shine the entire galaxy around them. These are quasars, lighthouses of the early universe. We see them shining from billions of light years away, their light beginning its journey when the universe was still young. It's a strange paradox, the darkest objects in the universe creating the brightest phenomena. But this brightness doesn't come from the black hole itself, it comes from the chaos just outside its edge. Finger time, the black hole may consume the disk and quiet down again, but its presence remains, a kind of gravitational anchor at the centre of galactic life. And the deeper we look, the more it seems that these black holes and their host galaxies are somehow linked, that as one grows, so does the other. Blackmail. But how? And why? That's the mystery we'll gently walk into next. Let's remain near the centre of the galaxy for a little while longer, where the stars curve in tight arcs and space itself feels stretched. We've met the supermassive black hole, a silent presence that hides at the heart of many galaxies. But now comes the quieter, more intricate question. How are these black holes connected to the galaxies that host them? Because strangely, beautifully, there is a relationship here. One so consistent that astronomers have given it a name, the M-sigma relation. It turns out that the mass of a galaxy's central black hole correlates with the velocity dispersion of stars in the surrounding galactic bulge. In simpler terms, the bigger the black hole, the faster nearby stars move, and the more massive the bulge tends to be. This is odd. The black hole is tiny compared to the galaxy. It accounts for a fraction of a percent of the galaxy's total mass. And yet, its size knows something about the stars far beyond its event horizon. It's as if a tree's root system could somehow determine the width of its canopy, without touching it. This connection suggests co-evolution, that galaxies and their black holes grow together, influencing one another over cosmic time. But how? Idea is feedback. When a black hole becomes active, when it feeds and blazes with X-rays, jets and light, it doesn't just shine, it pushes. The energy it releases stirs the gas in the galaxy, heating it, blowing it away, sometimes stopping new stars from forming. These outbursts, though brief in the grand timeline of the universe, act like punctuation marks, regulating growth, setting limits, shaping future structure. This AGN feedback might help explain why massive galaxies tend to stop forming stars earlier than their smaller cousins. The black hole, in its fury, quells the birth of stars. A cosmic fire that both warms and withholds. Some black holes even release relativistic jets, narrow beams of charged particles that erupt from their poles, travelling thousands of light years. These jets don't come from inside the black hole itself, nothing escapes that fate, but from the twisted magnetic fields just outside the event horizon. They slice through the galaxy, shaping clouds, compressing regions, even sparking star formation in some distant cases. Forging this tiny invisible point at the galaxy's core becomes a conductor, sometimes quiet, sometimes blaring, shaping the music of galactic evolution. It is strange to think that something so small, so hidden, can have such reach. But that's the nature of gravity, of energy, of time. A supermassive black hole doesn't simply sit at the center. It listens, it responds, and sometimes it roars.
Galaxies, like stars, live lives with phases. There's birth, growth, a kind of middle age. But for many galaxies, something curious happens. They grow quiet. They stop forming stars. The gas that once curled into luminous clouds no longer cools enough to collapse. The glowing nurseries dim. The bright blues of young stars fade, leaving only the older, redder ones to shine. And just like that, a galaxy becomes quenched. But what does it mean to quench a galaxy? It doesn't mean death. The stars still burn. The galaxy still rotates, still moves through space, still shines. But its future changes. It becomes quieter, more static. Its days of forming brilliant, massive stars are mostly behind it. This shift can happen slowly or suddenly. And astronomers have long wondered, what causes it? There isn't just one answer. There are several paths to quenching, and many of them are shaped by what the galaxy is doing or where it lives. One common cause is gas exhaustion. A galaxy uses up its cold gas, the fuel for star formation, faster than it can replenish it. This might happen after a starburst, or simply over billions of steady years. Without gas, stars can't form. It's like running out of wood for a fire. The heat remains, but the spark fades. Another path is gas heating. In larger galaxies, especially those near the centers of clusters, the inflowing gas can be heated to such high temperatures that it no longer cools efficiently. This hot halo gas just floats, never collapsing, never feeding new stars. The galaxy is surrounded by fuel it can't quite touch. And then there's feedback, that quiet but powerful process we met earlier. A supermassive black hole, during an active phase, can release jets and winds that sweep away gas or prevent it from cooling. This can shut down star formation across the galaxy, like a gust of wind blowing out a flame. Galaxies can also be stripped of their gas when they fall into clusters. As they move through the intra-cluster medium, the pressure can push gas out, ram pressure stripping again, leaving a galaxy without the raw materials to make stars. Entered each of these processes, on its own or in combination, nudges a galaxy towards stillness, toward that quiet state we call quenching. But here's something gentle to remember. Quenching isn't failure, it's transition. Some galaxies, like massive ellipticals, were quenched billions of years ago and still glow with quiet dignity. Others, perhaps the Milky Way, someday far from now, will follow that path. A gentle winding down, a slowing heartbeat. The cosmos, even stillness, has meaning.
Let's linger a little longer in this phase of stillness, the quiet after the storm. When a galaxy is quenched, it doesn't vanish. It simply changes tone. Think of a symphony that once played loud, joyful crescendos now slipping into a soft adagio. The tempo slows, the instruments thin out, but the melody, the structure, the shape of the music remains. For many galaxies, quenching means a turn toward structure and memory. The spiral arms may blur, their patterns fading without new stars to refresh their contrast. The bright blue lights of short-lived high-mass stars are gone. Left behind are the longer-lived reddish stars, steadier, fainter, older. This change is visible. Astronomers talk about the galaxy color magnitude diagram, a kind of cosmic census where galaxies fall into two broad categories: the blue cloud and the red sequence. Galaxies with active star formation tend to shine blue, young, bright and gas-rich. But quenched galaxies drift into the red sequence, dim, settled, quiet. Between these two is a transition zone we call the Green Valley. It's not a place but a phase, a gentle slope from youth to age, from gas to memory. A galaxy passing through this valley is changing. It may never form another star again. Or, under the right conditions, it might awaken once more. Because quenching isn't always forever. Some galaxies are rejuvenated. A new supply of gas might arrive, perhaps pulled from a passing filament or delivered by a minor merger. The once quiet galaxy stirs again. Stars begin to form, and slowly colour returns. Not as bright perhaps, not as chaotic, but alive nonetheless. This cyclical nature, growth, quiet, rebirth, is one of the most remarkable features of galaxy life. Nothing is wasted. Gas that doesn't form stars today might linger for eons before finding its way into a future sun. A star born now might light up a planet long after the galaxy's golden age has passed. And sometimes quenching allows us to see more clearly. In a star-forming galaxy, clouds and young stars can obscure the view of older structures. But in a quenched galaxy, the past stands more visible. The bulge, the halo, the remnant signatures of mergers long ago, they all linger in the light. These are fossil records in motion, not dead, but deeply reflective. Quenching isn't the end of a galaxy's life. It's the beginning of its memory. Let's return for a moment to the quiet breath of a galaxy, to the swirling disk, the drifting clouds of gas, the stars orbiting gently in their lanes. All of this motion seems governed by gravity, by mass, inertia, collapse. And it is. But there's another force at play, subtle, often overlooked, but always there like a soft current beneath the waves. Tism. Associate magnetic fields with galaxies. We tend to think of them on smaller scales. A compass needle pointing north, the hum of a transformer, the field around Earth that shields us from solar wind. But galaxies too have magnetic fields. Invisible threads stretching across tens of thousands of light years, shaping the motion of particles, guiding the flow of cosmic gas. These galactic magnetic fields are incredibly faint, millions of times weaker than a refrigerator magnet, and yet they matter. They arise from the same fundamental rules that govern stars and plasma. Most of the matter in galaxies exists not as solid material, but as ionized gas, plasma made of charged particles. And wherever you have moving charges, you can generate a magnetic field. When that gas swirls through galactic rotation, turbulence, supernova explosions, it creates currents, and those currents, in turn, amplify and sustain magnetic fields through a process called the galactic dynamo. It's like a slow, enormous electric engine, powered by rotation and chaos. These fields thread through the spiral arms of galaxies, following their graceful curves. They arc above and below the galactic plane, creating magnetic halos, and they weave through the interstellar medium, influencing how gas clouds collapse, or resist collapse, into stars. In that sense, magnetic fields act like a second skeleton, less obvious than gravity, but quietly shaping how galaxies move and evolve. Even star formation itself is affected. In regions where clouds are dense enough to form stars, magnetic fields can resist collapse, providing pressure that slows down the process. In other cases, they help channel material, guiding it into filaments where stars can more easily form. They don't replace gravity, but they complicate it. These fields also influence cosmic rays, high-energy particles racing through space. Magnetic fields bend their paths, trap them in loops, and carry them across galaxies. Without magnetic guidance, these particles would stream straight through space. Instead, they spiral, bounce and dance, sometimes for millions of years, within a galactic cocoon. It's a reminder that even in something as vast as a galaxy, the invisible forces matter. The faintest lines, the quietest pressures, the fields we can't see, these are part of the architecture. And though we only began to detect them properly in the last century, magnetic fields have been there since the beginning, since before the first stars, before the first galaxies, woven into the plasma of the early universe, shaped by turbulence, stretched by time. Garmin Station will explore what magnetic fields do between galaxies, how they thread through clusters, filaments, and perhaps even the cosmic web itself. We've seen how magnetic fields flow gently through galaxies, quietly influencing how stars are born, how gas collapses, and how cosmic rays wander. But these invisible threads don't end at the galactic edge. They stretch further, much further. Out beyond the spiral arms, beyond the halos of stars and dark matter, magnetic fields continue their quiet weaving. They link galaxies to clusters. They stretch across filaments of gas. They thread the very structure of the cosmic web. Intergalactic medium, the magnetic fields become even more mysterious. These intergalactic magnetic fields are extremely faint, billions of times weaker than the Earth's field, so faint, in fact, that we can't measure them directly. Instead, we detect them through their influence, on the polarization of light, on the bending of cosmic rays, on the delicate fingerprint they leave in the light of distant galaxies. The tool scientists use to study them is Faraday rotation. As light passes through a magnetized plasma, its polarization angle twists ever so slightly. By measuring this twist across many galaxies, astronomers can trace the strength and direction of magnetic fields between them. The results are subtle but revealing. They suggest the magnetic fields thread through galaxy clusters, often aligning with the shape of the hot gas that fills those clusters. These fields can help contain this gas, guide its motion, and even influence how galaxies behave as they fall into the cluster's heart. Flushing in filaments, the long, wispy connections of matter that link clusters across space, magnetic fields may play a role in how gas flows. They could act like cosmic guide wires, shaping not only the flow of material, but also how turbulence and shockwaves spread during structure formation. And even in the early universe, long before stars lit up the night, there may have been primordial magnetic fields seeded during inflation or phase transitions shortly after the Big Bang. These ancient fields, if confirmed, would be among the oldest surviving features in the universe, whispering across the void from a time before time had meaning. BJ, the story of magnetism in the universe is still unfolding. We don't fully understand where all these fields come from, or why they have the strengths and shapes they do. But we know this: they're not just afterthoughts. They are threads in the cosmic fabric, quiet, unseen, but deeply influential, without touching. They shape without shining. Blankets. They are the ghostly artists behind the dance of matter, energy, and light. Let's return now to the way galaxies help us see, not only across the cosmos, but across time itself. Because every galaxy you've ever glimpsed, whether in a telescope or in a softly glowing photo from space, has already changed. In fact, it changed long before you saw it. This is the strange gift of light. It carries not only what we see, but when we see it. Light travels fast, but not instantly. When it leaves a galaxy and begins its long journey toward us, it becomes a kind of time capsule. That light, uninterrupted for millions or billions of years, tells us what the galaxy looked like when that photon began its journey. And so, when we look out at the night sky, we are not just seeing distant places, we are seeing distant times. Some stars are already gone, some galaxies have merged or transformed, but the light from their earlier selves is only now brushing past your eyes. This idea of look-back time is more than a poetic turn of phrase, it's a scientific tool. For example, when we observe the Andromeda Galaxy, we're seeing it as it was over 2.5 million years ago, before humans even walked upright. We are watching it from the perspective of early ancestors who had yet to discover fire. If we look deeper, to galaxies a billion light years away, we're seeing into a time when Earth was still covered in primitive life, before trees, before birds, before mammals. And as we look farther still, to the faintest, most distant galaxies we can find, we begin to see the universe as it was only a few 100 million years after the Big Bang. Seismic dawn, a time of first light, when the earliest galaxies flickered into being. And through modern telescopes we can now glimpse that glow. Spastian telescopes like Hubble and James Webb act like deep-time archaeologists. They don't just see far, they see early. Each image is a slice of the universe's history, arranged not side by side, but stacked one behind the other like tree rings of light. Even the light itself tells us how far it has travelled. As space expands, it stretches the light that moves through it. This stretching shifts the light's colour toward the red end of the spectrum, a phenomenon called redshift. The more distant a galaxy, the more its light is redshifted, and the older the light must be. In this way, astronomers use redshift not just to measure distance, but to read the timeline of the universe as a page in a glowing book. And when you read its light, you turn not just across space, but across the past. So now you know, light carries time. But what happens when we gather enough of it? Enough galaxies, enough distances, enough histories? What begins to emerge is not just a gallery of glowing islands in space, but a kind of timeline, a record of how galaxies evolve, step by step. By studying galaxies at different distances, and thus different ages, we can begin to trace how they change. In the early universe, galaxies were small, clumpy, irregular. They spun less, they collided more. The cosmic environment was crowded and hot, and gas was plentiful. Star formation happened in frenzies. These galaxies shone brightly in ultraviolet light, the glow of hot young stars pouring into the dark. As time passed, the chaos cooled. Galaxies grew, both by forming stars and by merging with other galaxies. Spirals appeared, those elegant rotating disks, where angular momentum had time to sculpt shape from turbulence. Giant ellipticals began to form through mergers and collisions, especially in dense environments like clusters. With more time came more structure. Bars appeared across the centres of spiral galaxies, redistributing mass and gas. Some galaxies began to slow their star formation. Some went quiet altogether. Redder, older, more reflective. This progression, from blue and active to settled and red, is visible in the so-called galaxy colour mighty diagram, a kind of census of the universe's light. Young galaxies live in the blue cloud, while older, quieter ones inhabit the red sequence. In between, there's the green valley, a gentle transition from life to memory. But even this arc, this long journey of structure, doesn't always follow a simple path. Skyrocket are rejuvenated. A new stream of gas might arrive, or a minor merger might stir the pot. New stars flicker into being. The galaxy brightens again, if only briefly. Others, long quiet, drift gently into invisibility, fading as their oldest stars reach the end of their long, red lives. Shami, galaxy evolution is not a straight line, but a dance. A slow waltz of growth, rest, and renewal. A symphony of interactions, gravity, magnetism, radiation, all layered over time. And all of this, everything we know about how galaxies form, live, and change, comes not from seeing galaxies as they are now, but from seeing them as they were. Foreground. The audience. The patient observers. The ones who arrive late and sit quietly, listening to the echo of a universe that has been singing for billions of years. Punished, each photon that reaches us is not just an image. Fastball. It is a voice. It is a note. It is a chapter. And when you step outside on a clear night, you're not just looking up. Now that we've walked gently through the timeline of galaxies, their messy beginnings, their graceful middle years, their slow quieting, it's time to pull back once again, further, wider, themselves shrink to specks, until the luminous spirals and grand ellipticals blur into soft points of light. And then, slowly, the pattern emerges. This is the cosmic web, the vast three-dimensional structure of the universe itself, a shape formed not by individual galaxies, but by billions of them. A network stitched together by gravity and time, drawn by the hidden scaffolding of dark matter and illuminated by the stars that followed. It might be hard to imagine structure on such an enormous scale, but simulations and galaxy surveys show it clearly. The universe is not an even soup of matter and light. It's a sponge, a foam, a web. There are filaments, long glowing bridges where galaxies cluster like beads on a string. There are nodes, dense regions where these filaments cross, home to massive galaxy clusters. And there are voids, vast expanses of emptiness where few galaxies ever formed at all. Structure emerged from imperfection. In the earliest moments after the Big Bang, the universe was almost perfectly smooth, but not quite. Tiny fluctuations in density, seeded by quantum effects and stretched by cosmic inflation, created the blueprint. Regions just slightly denser than their neighbours attracted more matter. And over billions of years, those tiny seeds became clusters, galaxies, and filaments. It's the ultimate ripple effect. It's still happening. Galaxies continue to flow toward the denser parts of the web. Voids grow larger as matter is pulled away. And the whole structure slowly sharpens, drawn tighter by gravity, stretched further by the expansion of space. Look at large-scale maps of the universe, like those from the Sloan Digital Sky Survey. You can see it, the threads, the crossings, the empty spaces. It looks like biology, like a brain, like frost blooming across a window. Freezes. The universe at its largest scales is not chaotic. It's exquisitely organised. It doesn't look like randomness. It looks like memory. And in the next session, we'll trace how this structure evolves and how it might one day settle into its final form. Let's stay here, in this wide, quiet space between galaxies. We've pulled back far enough to see the threads of the universe, the vast filaments of matter, light, and memory that make up the cosmic web. But this structure isn't fixed. It changes, slowly, elegantly. Specillions of years, the cosmic web has continued to evolve, shaped by the competing forces of gravity and expansion. Gravity draws galaxies inward, toward clusters, toward filaments, toward the dense knots of dark matter that anchor the structure. But space itself is stretching, pulled outward by something even more mysterious: dark energy. Submerged gentle tension between coming together and growing apart defines the shape of the universe. In the present era, we see galaxies moving along filaments like raindrops running down a window pane. They drift toward clusters, join groups, fall into orbit. Entire filaments migrate slowly toward the nodes, building up the dense cities of galaxies we call superclusters. But even as these structures grow, the gaps between them widen. Voids become emptier, the cosmic web stretches. And in time, perhaps tens or hundreds of billions of years from now, that web will begin to thin, not collapse, not disappear, just settle. Positions of the web that are gravitationally bound, like our local group, will remain intact. The galaxies within them will merge, orbit, and glow softly for trillions of years. But the structures not bound together will fade from view, pushed beyond our cosmological horizon by the accelerating expansion of space. This future universe will still contain the same cosmic web, but much of it will lie beyond reach. Galaxies that are now visible in our telescopes will vanish, not in reality, but in visibility. Their light will never reach us again. It's as if the stage remains, but the curtains slowly close around it. Still, the pattern remains. Even in isolation, the local structures reflect the frozen memory of motion, the filaments etched into the orbits of stars, the clustering of galaxies that once moved together. The faint background of microwave light still glowing with the echo of the beginning. Unravel, but it will rest. Blackmail, and perhaps billions of years from now, someone will trace it in simulations or in fossil light and still see the same pattern. A whisper of filaments, a soft geometry drawn across time, the shape of everything. Let's step now, not backward, not outward, but gently forward, into the future. You follow galaxies from their beginnings, cumpy, wild, full of new stars. You've watched them settle, form spirals, collide, and go quiet. But their journey doesn't end in silence. The universe, even in its later chapters, still has stories to tell. To glimpse those future chapters, we need to look at two forces: gravity, which pulls things together, and dark energy, which stretches space apart. Let's start locally. Our Milky Way isn't alone. It's part of a loose family of galaxies called the Local Group, including Andromeda, the Magellanic Clouds, and dozens of smaller companions. And like quiet neighbours on the same country road, we're slowly drifting toward each other. Out 4 billion years, the Milky Way and Andromeda will meet. It won't be an explosive crash. Space is too spacious for that. Most stars will simply pass by one another, like dancers on an open floor. But the shapes of the galaxies will stretch, ripple and distort. Their gas will collide. New stars may briefly flare into life. Submerged, and after a long, slow dance, the two galaxies will merge into one. Astronomers already have a name for it: Milkomeda. This new galaxy will be bigger, rounder and calmer. A large elliptical system glowing with the light of ancient stars, a place of memory, not birth. Meanwhile, farther out, the rest of the universe is changing too. Blurred by dark energy, the expansion of space is accelerating. That means galaxies not bound into local groups or clusters are being carried away, not because they're moving through space, but because space itself is growing between us and them. Eventually, those galaxies will cross what we call the cosmic event horizon, a boundary beyond which their light can no longer reach us. Not because it's too dim or too slow, but because the space in between grows too fast. In the far future, perhaps 100 billion years from now, most galaxies in the sky will disappear, not in reality, just in visibility. The sky will grow emptier, the great cosmic web will stretch beyond perception. But that doesn't mean the story ends. Our little island of galaxies, life continues. The merged Milkomeda will still shine. Stars will still be born, slower now, dimmer, but born nonetheless. Planets will still orbit, light will still travel. Enjoys as the universe still holds what it can. And the stars, like the universe itself, still have time left.
Let's keep moving forward, slowly now, gently, into the farthest futures the mind can reach. Imagine a night sky billions of years from now. Quiet, dark, no swirling arms of distant galaxies, no tiny smudges beyond the local group, just the stars within Milkomeda. Old, steady, quietly burning out. Because eventually the universe doesn't end with a bang, it ends with a cooling breath. Over trillions of years, the fuel for star formation runs low. The hydrogen clouds that once collapsed into brilliant new stars are either gone or too warm to condense. Star formation fades. The last bright stars are born, and then there are no more. What's left behind are long-lived red dwarfs, stars that burn their fuel slowly and may shine for trillions of years. Eventually, even they will fade. The brightest stars, those we see now, the giants and the suns, will all be gone, leaving behind white dwarfs, neutron stars, and black holes. The galaxy will still exist, it will still move, but its light will grow dimmer, like embers cooling in the ashes of a great fire. Confiscated the era sometimes called the degenerate era, not because it's bad, but because matter itself becomes degenerate. White dwarfs and neutron stars are supported not by fusion, but by quantum pressure. They are the final flickers of structure. Stabilized black holes have a story in this far-off time. They do not last forever. Through a process called Hawking radiation, black holes slowly leak energy, an idea proposed by Stephen Hawking in the 1970s. Over incomprehensibly long timescales, 14,000 of years or more, black holes will evaporate, one by one, vanishing into soft puffs of particles. And then, universe becomes quiet in a deeper way. No more stars, no more galaxies, just dark, cold space. Particles drifting, occasional collisions, a a soft hum of background radiation stretching thinner and thinner. This isn't a moment of doom. It's a long exhale, a settling, the final rest after a very long journey. And yet, even in this ending, there's something beautiful. Breaking, because everything we see now, every galaxy, every star, every atom, had its part to play in this quiet finale. The universe lived fully. It expanded, it created, it warmed, it cooled. It dreamed, perhaps, through the minds of those who looked up at night and wondered. And so, even in the last darkness, there is still a kind of light. Position, one you can see.
After drifting through galaxies and light, time and gravity, let's come gently back to where we are now, to this pale blue world, to the very edge of a spiral arm, to a species that looks up at the stars and dares to ask, what is all of this? Salesman's Session is not about galaxies themselves. It's about how we know they exist, how we've come to understand the shape and history of a universe so vast, so old and so quiet that it seems almost designed to be unknowable. And yet, we know, representing, but enough to begin. Thinly of Galaxies began with a question about a smudge. In the 18th and 19th centuries, astronomers began cataloguing fuzzy, cloud-like patches in the sky. Some were nebulae, clouds of gas within our own galaxy, but others, like the Andromeda Nebula, held a secret. In 1924, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to resolve individual stars within Andromeda. That changed everything. Submerged, because if those were stars like our own, then Andromeda was not a nebula in our galaxy. It was a galaxy of its own, a separate island of stars far beyond the Milky Way. Suddenly the universe expanded, not just in size, but in meaning. That discovery lit a fire. We began measuring redshift, the way light stretches as objects move away from us. The farther a galaxy, the more its light is shifted toward the red end of the spectrum. Hubble discovered that the universe is expanding, and the more distant a galaxy, the faster it recedes. Unborn from redshift, we found velocity. From velocity and brightness, we found distance, and from there we began to build a map of the cosmos. But it didn't stop at measuring. We learned to listen. Unbiased to telescopes, we mapped the cold hydrogen gas in galaxies. With X-ray telescopes, we studied hot gas in clusters. With spectrometers, we decoded the chemistry of stars. And with gravitational lensing, we traced the presence of invisible mass, dark matter, by how it bent the light of more distant galaxies behind it. Peacefully added a layer, a texture, a whisper, discharged, and all of them depended not just on tools but on patterns. Astronomers look for relationships, how brightness relates to distance, how shape reflects age, how clustering reveals gravity's long hand. We don't watch the universe like a movie, we piece it together like a puzzle, using the snapshots light has given us. We also test. Through simulation, theory and observation, we refine what fits and discard what doesn't. It's not perfect, but it's resilient. Every discovery is checked against what came before, and if it doesn't fit, we ask better questions. Because science is not about certainty, it's about clarity, like slowly cleaning the lens on a telescope until the picture comes into view. Stabilizer's gigarity has given us a universe 13.8 billion years old, a web of hundreds of billions of galaxies, a fabric of space shaped by dark
and deserts, from satellites and labs, from people who stayed up late, staring into the dark, asking quietly, what else is out there? We'll continue this exploration soon by looking through the very tools that made it possible, Hubble, Webb, and what comes next. But for now, rest in the knowing that we can know, that we do know, and that the universe is not unknowable, it's just very, very patient. Let's lift our gaze to the instruments that have helped us see further, not just in distance, but in depth. To understand galaxies, to glimpse the early universe, we needed eyes that could reach beyond our atmosphere. We needed stillness, clarity, and patience, and we found it in the silence of space. The story begins with the Hubble Space Telescope. Launched in 1990, Hubble was the first major telescope placed beyond Earth's turbulent skies. From its perch above the atmosphere, it could see clearly, no atmospheric distortion, no clouds, no day or night, just an uninterrupted gaze into the vastness. At first, things didn't go smoothly. The telescope's primary mirror had a tiny flaw, a spherical aberration that blurred its images. But even this wasn't the end. Scientists engineered a solution, a corrective lens system installed during a space shuttle mission. It was, in essence, glasses for a telescope. Once corrected, Hubble began to transform our understanding of the cosmos. It photographed galaxies in exquisite detail, spirals, mergers, and ellipticals etched against black. It peered deep into the universe, capturing light that had travelled for billions of years. Its most famous image, the Hubble Deep Field, was taken by pointing the telescope at a seemingly empty patch of sky. What returned was a picture of thousands of galaxies, each one a glowing brushstroke in the painting of the cosmos. It was as if the universe had been waiting for someone to look deeply enough. Hubble helped refine the age of the universe. It traced the history of galaxy growth, the distribution of dark matter, the expansion rate of space. And it did so with instruments that could see not just in visible light, but in ultraviolet and near-infrared as well. Deeper we looked, the more we craved even earlier light, from a time before galaxies were fully formed, when stars were just beginning to shine. Balloons we needed a new eye. Enter the James Webb Space Telescope, a successor not just in time but in sensitivity and ambition. Unlike Hubble, which orbits Earth, Webb sits at Lagrange Point 2, a gravitationally quiet spot about 1.5 million kilometers away. There it stays cold and still, protected by a tennis court-sized sunshield and folded like a golden origami flower, designed to unfold and peer deeper into the infrared sky. Why infrared? Blackmail, because the oldest light in the universe has been stretched, red-shifted by the expansion of space. What began as ultraviolet or visible light now arrives as faint warmth. Webb can detect that warmth. It can see the earliest galaxies, the first stars, the slow assembly of structure itself. And as it does, it lets us look not only farther, but earlier. It builds a bridge across cosmic time. In the next session, we'll explore what Webb is beginning to show us, and what future instruments may reveal. Brian, because we're still looking, still building, still listening, and the sky is still answering.
Let's return now to the unfolding mirror of the James Webb Space Telescope, golden, silent, suspended in the dark. Webb is not simply a replacement for Hubble, it is a different kind of listener. While Hubble captured starlight as we see it, Webb catches the faint warmth of the earliest galaxies, the ones born when the universe was still wrapped in its first few 100 million years. This is not easy light to see. Conserve redshifted beyond the visible, stretched across time by the expanding fabric of space. To detect it, Webb must be cold, very cold. Its instruments operate just a few degrees above absolute zero. Only in that stillness can it sense the subtle glow of galaxies forming in the long-ago dark. Swallowing, Webb has delivered. It has found galaxies older than we expected, dense, bright systems that appeared when the universe was barely 300 million years old. It's challenging our models of how quickly stars and galaxies formed. It's helping us revise the story, not because the old version was wrong, but because the new version is more detailed, more vivid, more real. Is also looking closer to home, studying exoplanets, worlds orbiting other stars. With its powerful spectrometers, it can sniff the atmospheres of these distant planets, searching for signatures of chemistry, and perhaps one day, something more. This is one of the most profound aspects of astronomy. The same tools that look into the past can also look into the possibility of life. Prominently as Webb opens new windows, we are already thinking of what comes next. Missions like Nancy Grace Roman Space Telescope, set to launch later this decade, will broaden our view of dark energy, galaxy formation, and the structure of space itself. It will offer a wide-field view of the universe, like Hubble, but 100 times more sky in every shot. Further on, concepts like LUVOIR and HABEX are being explored. These would combine Hubble's sharpness with Webb's sensitivity and add the ability to directly image Earth-like planets around nearby stars. Imagine that, seeing a pale dot nestled in a sunbeam not so different from our own world. Blindness where someone might also be building telescopes. That's the quiet magic of our instruments. They are not just machines, they are extensions of wonder. They take the silent, steady reaching of human curiosity and carry it beyond the sky, beyond the past, beyond the limits of light itself, unlocking outward. Pedestrians, and in doing so we understand ourselves. Let's turn now from the telescopes that look outward to the ones we build inward. Because not all discoveries come from light. Some come from code, from simulations so detailed, so rich, they can recreate galaxies, clusters, even cosmic web filaments, all within a computer. These are not animations. They are not just visualizations for beauty's sake. They are simulated universes, built from physics, statistics, and mathematics. They follow the laws of nature as we understand them, and they let us watch the cosmos unfold, frame by frame. Imagine you start with a small cube, say a region of space a few 100 million light-years across. You fill it with dark matter particles and gas based on what we know from the early universe. You let gravity act. You include the cooling of gas, the formation of stars, the explosions of supernovae, the jets from black holes, blackmail, propane. Merges, over billions of simulated years, is a universe that looks startlingly real. Line galaxies form in dark matter halos. Clusters emerge at the intersections of filaments. The cosmic web sharpens and grows. You can pause at any moment, zoom in on a spiral arm, and watch it wind. These simulations help us answer questions that observation alone can't. Why do galaxies form where they do? What determines their shape, size, or colour? Why do some go quiet early, while others shine on? Famous simulations is the Illustris project, followed by Illustris TNG, next-generation models that added more detailed physics. These simulations didn't just create realistic galaxies, they also modelled feedback, how stars and black holes shake their environments. Galaxies that look not only realistic, but statistically similar to what we actually observe. Platinum, this is a quiet confirmation. When our simulated universes resemble the real one, it suggests our physics is on the right track. It doesn't prove we're right, but it helps us see where we're wrong. And that's part of the magic. Simulations let us run the universe again, tweaking one variable at a time. What happens if we add more dark matter? If black holes feed more aggressively? If gas cools faster? We can explore alternate paths, parallel histories, even test the edge of known laws. It's not unlike weather forecasting, except the weather spans cosmic time, and the outcomes include entire galaxies. We'll talk about resolution, limitations, and the strange intimacy of building a universe with numbers. Because behind every simulated star, a human mind dreaming with physics. Let's step deeper now into that digital cosmos. A simulated universe is, in some ways, a paradox. It's made of nothing, just math, code, and time. And yet from those abstractions emerge structures that look and behave like galaxies, clusters, and filaments. In silence and lines of logic, the cosmos begins again. But building these simulations isn't just about imagination, it's about resolution. Just as a high-resolution photograph shows more detail than a pixelated one, simulations also have their limits. You can't model every star, every atom, not yet. Instead, you make trade-offs. You group matter into particles, each representing thousands or millions of real things. You smooth over small-scale chaos to capture the large-scale shape. And higher the resolution, the more computing power you need. Some simulations require supercomputers running for weeks or months. They're parallelized, distributed, broken into tasks spread across thousands of processors. And even then, choices must be made, what to simplify, what to prioritize. It's not unlike painting a landscape. Do you focus on every leaf or on the shape of the forest? What emerges is not a single answer, but a tool for testing. For instance, when simulations include feedback from black holes, they better reproduce the population of red, quenched galaxies we see in surveys. When they adjust how fast gas cools, they change how quickly stars appear. By comparing outcomes to real data, we refine our models, we learn. Simulations also let us explore extremes. What if dark matter behaved differently? What if there were no black holes? What happens to galaxy growth in a universe without feedback, or with more violent early structure? These are not idle experiments. They help us define the boundaries of what's possible. There's something oddly intimate about this process. You start with equations that govern the cosmos, Newton, Einstein, quantum mechanics. You translate them into algorithms. You feed them into a machine. And then, somewhere between the loops and the time steps, a galaxy spins. Deactivated. You told it to. Confiscates the laws led it there. Subordinate, its reflection. A mirror made of numbers. And in that mirror we glimpse a truth, that the universe, for all its vastness, is governed by laws so consistent they can be whispered into silicon and heard as spiral arms. Of course, simulations aren't perfect. They simplify, they assume, they sometimes miss the nuance of real gas, real dust, real chaos.
Upholstery, they let us try again. To rewind cosmic time, to tinker with gravity, to ask not only what is, but what could have been. And doing so, we become not just observers of the universe, but its quiet students. The odd.
Let's close our eyes now, not to sleep, but to see more clearly. You've wandered through galaxies, filaments and folds of space. You've listened to ancient light and watched stars flicker into being and burn out again. You've followed the slow music of gravity, the silence of dark matter, the gentle reach of magnetic fields, and through it all there's been a quiet presence behind the lens. You. Tori. The birth of galaxies, the shape of the cosmos, the long arc of time, has meaning only when it's held in a mind that asks. Astronomy is not just science, it is perspective. Displaced is to admit how small we are, but also how rare it is to be small and aware. You are made of atoms that once drifted through the arms of a galaxy. Hydrogen born in the Big Bang, carbon cooked in stars, iron forged in supernovae. You are not separate from the cosmos. Blackmail of a quiet fold in it, a ripple that looks back. Kang Sagan once said, "We are a way for the universe to know itself." And perhaps that's the most poetic truth of all, that galaxies swirl, stars shine, and somewhere on a small rocky planet one species asked, why? Asked, but listened. In asking where galaxies come from, we learn where we come from. In wondering how galaxies die, we glimpse our own finite story. And in watching the sky deepen, we begin to understand something soft and vast. That meaning doesn't come from scale. It comes from attention. Conflicting, and you have been attentive. You've travelled across billions of years tonight without leaving your bed. You've traced light older than language. And now, as you rest, perhaps with stars still gently turning behind your eyes, know this. You are stardust, yes. Bisexual. And you are also a witness. And feasting, you've made the universe just a little more complete. And now, at the edge of the cosmos, we pause. Not to ask another question, not to chase another fact, but to simply breathe with the universe. You've spent time tonight with galaxies, those vast, drifting structures of light and memory. You've watched them grow from clouds and filaments, form arms and halos, collide and merge, and slowly settle into stillness. You've seen them quenched, reignited, dimmed by time, carried away by expansion. And now, in the hush of your own evening, you're still here, gently orbiting your own centre, just like they do. To galaxies that we rarely speak of, we focus on their movement, their birth, their distant light, but much of their lives are spent doing nothing, loudly rotating, waiting, letting stars form and fade in slow cycles. No urgency, no race, just quiet endurance. You too are allowed to be still. We live in a world of velocity, of noise, alerts and ticking clocks. But you are also a biological galaxy, a being of swirling rhythms and long arcs. Your breath moves like a spiral arm, outward then inward again. Your thoughts drift like stardust. You don't need to explain everything tonight. Can simply exist. They don't rush toward conclusions. They become what they are over billions of years. Through trial and gravity and time, so do we. Foreground. And just as every galaxy carries its own shape, sculpted by collisions and quiet turns, you carry yours. Formed by moments, by choices, by little bursts of energy and long periods of reflection. Sometimes luminous, sometimes dim, but always turning. If you feel lost times. Remember, galaxy arms get warped, their centres shift. They spin alone in cold, dark space, and yet they shine. Not for anyone in particular, not for applause, but simply because that's what they do. You too have that light in you. And when you lay quietly, right now, maybe head resting softly, body sinking into the fabric of night, you are part of the stillness. Submerged from it, not smaller than it, just quietly belonging. And now, dear Star Watcher, the journey comes to rest. We've travelled billions of light years tonight.
Not with engines or rockets, but with wonder, quietly, slowly, like starlight itself. We've drifted with galaxies, floated through filaments, and lingered beside sleeping black holes. We've followed the threads of magnetic fields, decoded redshifts, and traced the flicker of stars long gone, all from the stillness of your own corner of the cosmos. And now, that stillness deepens. The room around you softens. Maybe your limbs feel heavy, like they're made of quiet stone. Maybe your thoughts drift, not sharply but gently, like leaves on a slow river. That's okay. That's part of the process. Because the universe, for all its grand patterns and powerful forces, also knows how to rest. Terminator does so every night, above your head. Even galaxies, those luminous cities of stars, spend eons simply being, rotating in silence, holding light and dust, waiting for nothing in particular. You are allowed that too. You are not just in the universe, you are of it. Flooring in your blood came from ancient supernovae, the calcium in your bones from long-dead stars. The hydrogen in every breath is the same that lit the first suns. You belong here, not in some grand epic way, but in the quiet way of galaxies, not asking to be seen, not needing to explain, just glowing softly in your own rhythm. So before you drift off, before sleep folds itself over you like a nebula, know this. Ambiguity, welcome to carry all the questions tonight. Unprotected need to solve the universe. Stabilized, you've listened, you've wondered. And now, you can rest. Discharge the galaxies, keep watch for a while. Let the stars hold your place in the sky. And when you dream, may you dream of light taking its time. Good night, Star Watcher. Discharged peacefully, wherever and whenever you may be.